Welcome back to our heat transfer class, where we will delve into the transfer of energy due to a temperature difference. This video was made with the support of Energy. Remember that the introduction to heat transfer is divided into several lessons. In the fifth lesson, you can find a description of the rate equation for conduction. That is, the Fourier's law. A consequence of Fourier's law is that the heat flux vector is normal at any point to the isothermal surfaces. However, for applying Fourier's law, you need to know the temperature derivative. In this sixth lesson, we're about to discover the secrets of how to find the temperature distribution inside a solid. This is made by solving the diffusion equation. One of Fourier's great contributions has been the deduction of the partial differential equation that governs the diffusion of heat and its resolution using series. The Fourier's series. This lesson is divided into several parts. Let's start analyzing the one-dimensional conduction.
We are going to use again the laterally isolated cylinder to force a one-dimensional heat flow. For a complete analysis of the conduction, we assume that there is a volumetric heat generation inside it. For example, because an electric current passes that generates heat by the Joule effect. This volumetric generation G is evaluated in watts per cubic meter. The left side is at a uniform temperature, T1, and the right side at a uniform temperature, T2. Let us take a differential control volume of cross-section AC and length dx. There will be a conductive inflow on the left face of the control volume and an outflow on the right face of the control volume. The application of the conservation equation tells us that inputs plus generation minus outputs equal to stored or accumulated energy per unit time. Now, we have to evaluate each of these components of the energy balance. The generated heat transfer rate, e.g., will simply be the product of the volumetric heat generation multiplied by the volume. If there is no phase change, the change in internal energy or accumulated energy per unit time is the mass times the specific heat multiplied by the change in temperature with time. In this expression, mass is written as density times volume. Now, we must evaluate inputs and outputs. Because the solid is a closed system, energy only enters or leaves the control volume through conduction. The input is the heat flux through the cross-section in X. The output is the heat transfer rate at X plus dx. We can express it as the heat transfer rate at X plus the derivative of Qx with respect to X times differential of X. After that, we get the expression of input minutes output components. We apply Fourier's law and we have the evaluation of this difference as a function of the derivative of t with respect to x. We can now substitute each of the terms in the energy conservation equation. The volume AC times dx, which appears in all terms, can be removed. Thus, we obtain an equation which is the heat diffusion equation for one-dimensional conduction. Notice that it is actually the balance of heat per unit volume within a solid.
After the deduction for a one-dimensional conduction of the diffusion equation, we can generalize for three dimensions.
In the x direction, we use the result of the input minus output component we found when applying the energy conservation equation for one-dimensional convection. We can substitute the heat flux using the Fourier's law. The cross-sectional area in this direction is dy times dz. In the y direction, the cross-sectional area is dx times dz. In the z direction, the cross-sectional area is dx times dy. After completing the analysis of inputs and outputs by conduction, we can add the internal generation and the storage terms. By substituting all the energy terms into the conservation equation, the volume can be omitted. The application of the energy conservation equation inside a solid gives the heat diffusion equation. As you can see, the heat diffusion equation is an energy balance inside a solid to which we have applied the Fourier's law to evaluate conduction fluxes. Therefore, when you will apply the heat diffusion equation, remember that the point of departure has been this energy balance. Solving this differential equation in partial derivatives, you can find the temperature field. Knowing the temperature field and applying Fourier's law, you can calculate the heat flux at any point in the solid.
The problem with this equation is its complexity, which led Fourier to develop the Fourier series to obtain an approximate solution. Let's analyze which simplifications we can do for obtaining analytical solutions of the heat diffusion equation.
For the steady state, the storage term is 0. For one-dimensional conduction, the derivative of T in two of the dimensions of the space are also 0. This is the diffusion equation for one-dimensional conduction in steady state. If the thermal conductivity is uniform and constant. For solids without internal heat generation, this is the Laplace equation for temperature. Let's apply the diffusion equation for a simple problem. For a laterally insulated cylinder without internal heat generation, calculate the heat transfer rate between the two extremes with the following conditions and data. Stop the video now and try to solve this exercise. Did you succeeded? Because this is a solid of constant section, without internal heat generation, with constant thermal conductivity and in the steady state, we can apply the Laplace equation. It is an ordinary second-order differential equation. Integrating once, we see that the derivative is constant. Therefore, the first consequence for this type of system is that the temperature distribution is a straight line. From the boundary condition at x equals 0, we deduce that C2 is equal to T1. From the boundary condition at x equals L, we can find the expression of C1 as a function of the temperatures and the length of the cylinder. Combining all these results, we obtain T as a function of x. Let us calculate the heat transfer rate. Once we have the expression for the temperature profile, we can find the derivative and apply Fourier's law. Substituting the values of the statement in the expression of the heat flux, we find the result. Did you obtain the same results?
We can generalize the results of the previous example for the temperature profile and the heat flux for flat walls.
As can be seen in the figure, for the previous exercise, the isothermal surfaces are parallel planes. These results can be applied for any system fulfilling the following conditions. Constant cross-sectional area like flat walls or cylinders in the axial direction. One-dimensional heat flow. In a stationary state. With uniform and constant thermal conductivity. Without internal heat generation. That is, when the Laplace equation for temperature can be applied.
The heat equation may also be expressed in cylindrical coordinates.
You can see that this equation is even more complex than the one in rectangular coordinates. For one-dimensional conduction in the radial direction, we assume that there are not variations in temperatures in both the angle direction and the axial direction. If the cylinder or the cylindrical wall is in a steady state, the diffusion equation is also a second-order differential equation, which is easy to integrate.
The heat diffusion equation may also be expressed in spherical coordinates, the radius, the zenith angle, and the azimuth angle.
For one-dimensional conduction in the radius direction. In a steady state. The diffusion equation is also a second-order ordinary differential equation. For radial systems, that is, with one-dimensional conduction in the radius direction and in a steady state, you can use these second-order ordinary differential equations.